All right. I apologize in this video if there are any announcements or any buzzing that comes out. They're apparently working on the overhead, the speakers there, so we'll just muscle on through them. So periodic trends are the idea that we can look at the way elements are placed on the periodic table. We can try and piece out some of the properties of those elements, of atoms of those elements anyways. And the first one is atomic radius. And you may have been taught way back when in some form of math class that if I take and I draw a dot, and we're going to have a dot right there, good, and I draw a circle around that, right? You perhaps at one point in time were taught that the radius of this circle is the distance from that dot, the center of that circle, to the outside of that circle. But the problem that we have in chemistry is that's great for a drawing, but we're not drawing atoms here. Atoms actually exist. And so it's not possible for us to measure the center of the atom, which, by the way, in case you don't remember, is called the nucleus, and measure the outside of the atom. Remember, what occurs on the outside of the atom here is little electrons, right? And so we've got electrons here on the inside, we've got electrons here on the outside. And something we're going to talk about in a later lesson is we're going to talk about how difficult it is to tell these electrons from these electrons. And so as a chemist, it's really hard for us to say, oh, atomic radius is just from the center of this circle or sphere, because remember, these are three-dimensional, they're actually spheres, but the center of that sphere to the outside of that sphere. Well, how do we find the center? How do we find the outside? Those are often measured using, two different means. So we can't really measure this like this. So what we do with atomic radius, I'm going to tell you, the actual definition of atomic radius is if I imagine I have two of these atoms and they're sitting side by side, right? If I'm looking into a sample of this atom, of this element, I should say, and there's a bunch of atoms inside there, and some of them are side by side, then you can see, right, we can imagine that the atomic radius here is half the distance between these two nuclei. And so that is it. That is the technical definition of atomic radius, which, by the way, the shortcut for atomic radius is AR. It's not assault rifle. It is AR. All right. In chemistry, we use AR to mean atomic radius. So atomic radius is the distance, it's technically half the shortest distance between two nuclei. Only one I in nuclei. There we go. Nuclei is the plural of nucleus. Okay. Shortest distance between two nuclei in a pure sample of an element. So literally the way we find atomic radius is they take a pure sample, they actually hit it with X-rays, and the X-rays scatter in a certain way, and we can tell exactly how far the nuclei are in that sample. Once we know that, half of that distance then becomes the atomic radius. And what you see here is atomic radius as it pertains to a column on the periodic table and a row on the periodic table. And so a great reminder here is we need to remind ourselves of what column and what row we're looking at on the periodic table here. So, by the way, if you ever need a periodic table on the fly, ptable.com, great place to find it. And you'll see right here, it comes in these nice colors, just a really nice website. They are paying me nothing to tell you that, okay? I just like this website. Plus, it's easy to remember, ptable.com. But anyways, we are looking for Li, Na, and K, and they're probably all in the same column, and they sure are. They are in this column right here, this first column. And then if you look, we've got K, Ca, Ga, and there's this weird looking gap here. Well, if you look, there's K, there's Ca, oh, there's a huge gap, and then Ga. Okay, so that tells me that what we're looking at is the fourth row on the periodic table as well. So this column up here, in case you don't remember, a column on the periodic table is called a group. So this is group 1. There's group 1. And then this one down here is period 4, was what that one was. I feel like there was a way to rotate these, but you know what? I don't know what it is. So we're just going to leave it straight up and down, just like that. All right? All right, so what we do is in periodic trends, we talk about what is the trend as I move down this group, okay? So we're going to take, and we're going to draw an arrow here. We're going to go down this group, all right? And we also talk about what is the trend as I go across this period. And I really like this image because this is somebody who has drawn an image of the atoms of these elements. And they've done that based off of this number right here, which is a real number, which was measured in a sample of lithium that's half the distance between the two closest nuclei of lithium. So that is a spherical representation, and it's beautifully drawn, and you know it's beautifully drawn because that means I didn't draw it, right? That's, you know, that's just plain simple fact right there, right? But this is a sphere of lithium, a sphere of atom of sodium, and there's potassium, Li-Na-K, or lithium, sodium, potassium, of course. Don't expect you to memorize that, but it's real easy to look at this and to tell exactly what's happening to the atom as we move down, right? The atom is getting bigger, and that means that its radius is increasing. And to further prove that, we can look at the numbers as we go from lithium 152, we go up to 186 and up to 227. So as you go down a group, atomic radius, AR, increases. And it's also fairly obvious as we look here. We can look at the pictures or we can look at the numbers, and you can see in a general trend as we move across the period, atomic radius decreases. Now the reasoning for that is, all right, the reasoning here is as I move from lithium to potassium, what's actually happening here is I'm getting more electrons. Lithium has 3 electrons, which are put into 2 levels, which is why it's on the second periodic table. Potassium has 19 electrons put into 4 levels. So there are more levels, there are more electrons in potassium, so they spread out and take up more space than the atoms of lithium do. So potassium has larger atoms than lithium. When you move across a table, you're staying in the same period, so you have the same number of energy levels, but what you're seeing is there are 19 protons in potassium, and there are 36 protons in krypton. So because there are more protons, they can pull the electrons in tighter. And so that's why krypton is smaller than potassium. You don't really need to know the explanation, but there is a reason for it. There is actual logic behind it. Or so the theory goes. So as you go down the group, atomic radius increases. As you go across a period, atomic radius decreases. All right, that's atomic radius. Ionization energy, again, to draw the atom. Here we've got our atom, and I'm going to put a nucleus right in smack dab in the middle of that thing. It's going to be, you know, just a dot. There we go. There's our nucleus. What ionization energy is? Oh, and don't forget we've got an electron out here in the outer shell. What ionization energy actually is what it takes for us to come in and yeet this electron on out of here. So ionization energy, which, you know, chemists, we're wonderfully unimaginative people. The abbreviation for ionization energy is IE. Ionization energy is the energy required to remove an electron from an atom. So this is another thing we can measure, right? They can take an atom, or at least a sample of atoms. They can remove the electrons from it, and they can measure how much energy it takes to remove those electrons. And one thing I don't like about this diagram is as you're looking at it, these spheres don't make sense. What actually you see on this diagram is it's the same exact spheres that are up above, just so that we can see what's the size of the atom. All right? And the numbers underneath it are what we need to look at here. So this number is what's the important thing that we need to look at. And as you look going down, I'm going to scroll this up just a little bit more there. There we go. As you look going down the group, right? So we're going to have to go down this group, and we're going again across the period here. As you go down the group, what's happening to ionization energy? Well, this one's 520, 496, 419. Well, the trend there is ionization energy decreases. Not sure why the R didn't take there. Decreases. There we go. There's a weird spot on my screen where I can't draw. Ionization energy decreases as you go down a group. All right. As we go across a period, what happens to ionization energy? Again, the spheres don't make too much sense, but if you look at the numbers, and there's also this weirdness right here. Look at this number right here. What's happening with calcium from potassium? If you only looked at these two, you say, oh, it goes down. But look in general, look all the way across. It does briefly go down, but then starts to go back up. This is a weird thing. This is a weird thing, and there is a reason for that, but we're not going to get into that in Chemistry 1, all right? There is a reason this ionization energy drops, but it's weird, and so we're not going to talk about it. But what we are going to talk about is what is the general trend. Well, if you ignore that exception, the general trend is that as you move across a period, ionization energy increases. And again, there is, oh, that is a horribly drawn S, but you know, there we go. Just make it better S. There we go. Increases. There we go. So there is a reason for this, okay? And the reason for that is if I look in lithium, there's the proton, there's the electron. In potassium, there's the proton, there's the electron. It's easier to remove this electron, it's easier to remove this electron, there we go, because it's a little further away from the nucleus. That's literally the reasoning for it. When we look at going across a period, well, you're saying, well, what? It makes sense again. This electron has gotten closer to the nucleus again. And remember, the reason it got closer is there's that pull. The pull is stronger on this side from the nucleus because there's more protons here. And so, therefore, it's harder to remove that electron. Makes things nice and simple. One thing I want you to notice, let's make a note of here. I'm going to make a note like right here. I'm just going to draw it to the side. You can put a text box here if you want. I might put this one in like gold or red or something like that, right? In fact, hey, let's make it, I don't want to make it yellow. Yeah, the yellow is really tough to read. Just take my word for it. So atomic radius and ionization energy. I don't know why I didn't write the I first. There you go. Atomic radius and ionization energy. What can we say about them? They are, well, let's look. As I go down, ionization energy decreases, but atomic radius increases. And as I go across, atomic radius decreases, but ionization energy increases. They are direct opposites. Atomic radius and ionization energy are opposites of one another. So if you memorize one, you can memorize the other one. In fact, all I really ever memorize is the fact that atomic radius, as you go down a group, it increases. Then I remember going across a period is opposite. And if I remember those two things for atomic radius, right, now I can figure out what ionization energy is because they're the exact opposite. It's pretty cool. All right. Last but not least, we have electronegativity. And electronegativity is the weirdest one of all of them, but it is a measured quantity. And the way this is measured is it is the ability of an atom of an element to remove an electron from another element. Okay. So the way, oh, by the way, I forgot to, I'll add this to the beginning here. Don't know why it's not going to let me. Don't forget, these all have shortcuts, right? The shortcut for electronegativity is capital EN. But electronegativity, literally, the way they test this is you'll take, an atom of sodium and an atom of carbon, you'll put them together, and you'll see which one pulls the electron away. And they rank them all. And this chart's kind of neat because it goes in a, you can see it's sort of meant to be a three-dimensional kind of thing, kind of popping out at you. And there's a couple of things to notice about it. First of all, the group numbers are at the bottom. They have to be at the bottom because up at the top, right, it's three-dimensional. You wouldn't be able to see them. So all the group numbers are down here. And you notice they use this old systems in here. We don't use group numbers like 1A, 2A, and 3A, 3B, yada, yada, yada anymore. We use these other group numbers. They just put them in parentheses. Not exactly sure why. Most people don't usually do that. But there's the group numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 16, 17. Wait a fudging minute. hold on, there's not 17. The first thing I always notice about this table is group 18 is missing. And the reason for that is, in electronegativity, the group 18 elements are all really close to 0. Very, very close to 0. So group 18 is left off of this chart because they're all very, very close to 0. And actually, I believe if you go over here and click on one of these elements, you can look up here. There's electronegativity. It says xenon is 2.6. This one might be using a slightly different. Oh, there we go. If you click on argon, not available. Neon, not available. Right. Some of these are really hard to measure. And it's not 3.0. Might need to contact somebody about that one. Oh, my beautiful tables might have some errors in it. But anyways, we just assume all of these guys are really close to 0. They are not gonna pull electrons from other elements. Up above here, I've left a box because it is important to one of the most important ones. And you notice if you look at it, it is the tallest element here. Fluorine is the element with the highest one. And it is set at 4.0. Now, why did they pick 4.0? I'm not sure, but they did that a long time ago, and now every element just gets compared back to fluorine. Group 18 is, so the only two you need to memorize are the fact that group 18 are not, right? They have 0 electronegativity, and fluorine is set at 4.0. Everything else, the way they find this is literally by comparison. You put two atoms together, and you'll see which one steals the electrons from the other one. And again, we can look at this. We can go down a group. We can go across a period. And that's a lot more fun when it's three-dimensional like this. But if we go down this group, it's really tough to look at like lithium to francium and see that one. But if you can look at any group you want. I love looking at group 17 out here, this one with fluorine. It's very clear what's happening there. As you go down this group, electronegativity decreases. And as I go across, you can pick anything you want, but it's really especially evident over here. Hey, look at that period 2. As we go across period 2, what's happening? Well, it's like stairs. We are rising, so there, electronegativity. Ooh, it's tough to write sideways like that. Electronegativity here is increasing. Electronegativity increases. See if I can make that a little nicer looking. No, I made it worse. Okay, sorry about that, folks. I will make that in. I will make it legible. But anyways, so here, let's look at this. Okay, so if I'm looking at electronegativity versus ionization energy, or, for example, oh man, I made it worse. All right, sorry, folks. Electronegativity here is increasing. So let's compare this to ionization energy, right? Ionization energy decreases as you go down a group. Electronegativity decreases as you go down a group. Ionization energy increases as you go across. Electronegativity increases as you go across. With an exception, don't forget, group 18 is an exception to that, right? Group 18 is 0. So on here I'm going to write, if all I have to memorize then is that electronegativity is the same as ionization energy. And that they are both opposites of atomic radius. Easy way to memorize all three. Electronegativity and ionization energy are the same. Atomic radius is not. It is the opposite of the other two, which is kind of neat. So how do you use this? Well, if you look down here, we got a nice blank periodic table. I'm going to pick two elements off the real periodic table, two I like, nice and alliterative, beryllium and barium. So if we look at where beryllium and barium are, beryllium's here, and barium's down here. And so if I want to compare their atomic radiuses, for example, well, we look at beryllium. Beryllium's at the top, barium's at the bottom. Remember, atomic radius. Scan back up there real quick. As we go down the table, atomic radius increases. So which one's bigger? Well, we increase going from beryllium to barium. So barium has to be bigger than beryllium. So a shorthand way to do that is just put the greater than sign pointing to barium. I always love to remember my 6th grade teacher taught us, this looks like Pac-Man. He always eats the bigger one, right? So barium greater than beryllium. But then you remember for both ionization energy and electronegativity, because it's backwards, right? If atomic radius increase is going down, ionization energy and electronegativity both decrease going down. So now instead we'll have beryllium is bigger than barium. It has higher ionization energy. It also has a higher electronegativity. Although if you look at that chart, it's kind of vast. It's kind of hard to read that. Don't really need to know the numbers. I just know the electronegativity of beryllium. I expect it to be higher than barium. Let's pick two other ones, two other alliterative ones, and that would be strontium and tin, for example. So we're going to go back here and we're going to put in strontium, like strontium is right here, and tin is over here. Notice they're in the same period. So if I want to compare those two, if I look at atomic radius, remember what happens to atomic radius as you go across. Atomic radius decreases. So which one's bigger here? Well, strontium is going to be bigger than tin. It's going to have a larger atomic radius. And then for ionization energy and electronegativity, I just remember that those are opposite. I know that tin has to have a larger ionization energy than strontium, and it also has to have a larger electronegativity. Easy enough. Can you compare ones that are diagonal? You can, but things get a little difficult. And hopefully we'll get a chance to address that tomorrow.